Hello students, I welcome you in today's session of physics, and today I am going to present you refraction of light at spherical surface lenses. This is your chapter number 16 of your unit optics. Clear? So here you can see this is the topic of coordinate geometry sign convention for measuring distances and lengths. In order to obtain common formula for the position and sizes of real and virtual images. I hope you know very well what are the real images and what are the virtual images you study in the previous classes, formed by the convex and concave lenses. Clear? So we have to adopt a common convention for giving signs, whether it is positive or negative here, to distance and lengths of the objects and the image and to the focal length of the lenses. Different writers use different sign convention, but most of them prefer coordinate geometry sign convention. Which sign convention we use here? Coordinate geometry sign convention. What says that? It states as below. The first one is the optical center of the lens is taken as origin. Clear? And the principal axis of the lens is taken as the x-axis. A line passing through the optical center and the perpendicular to the principal axis is taken as y-axis. I hope you know it. Now we will move to the second one. All the distances are measured from the optical center. We measure all the distances from which center? It is known as the optical center and the principal axis and perpendicular to it as follow. So here these are the two things given here, how you measure the distances from the lenses in the positive direction and in the negative direction as well. So the first one is says distance measured to the right of the optical center, that is your along positive x-axis, are taken as positive. Means if you move in the positive x-axis, then all the distances you are measuring are taken as positive, and the distance measured to the left of the optical center, that is if you are moving in the negative x-axis direction, then all the distances you take as a negative. Fine. Now the second one, distance measured upward from the principal axis are taken as positive. Same thing happen if you move in the y-axis upward direction and downward direction. So if you move upward from the principal axis, we take as positive, and those measured downward are taken as negative. Fine. According to this convention, the radius of curvature of convex surfaces and the focal length of a convex lens are taken as positive. So here the radius of curvature of convex surfaces and the focal length of convex lens are taken as positive. I hope you know very well what is the radius of curvature, what is focal length. These all things we had covered in our previous chapter. Fine. So I think I don't need to repeat again here. While those of a convex surfaces and a convex lens are taken negative. So you should keep in mind that the distances for the convex lenses are taken as positive. Clear? Whether it is for the radius of curvature or for the focal length. All these distances we take for the convex lens here as positive. Fine. While if we talk about the convex surfaces, then all the distances are taken as a negative here. I hope it is clear. Now we will come to refraction at concave spherical surface. So as you can see here, this is the figure we have to discuss here. You can see here in the figure 1 be a concave spherical surface separating a rarer medium of absolute refractive index N1, fine, from a denser medium whose absolute refractive index is how much? N2. Clear? You can see here P is the pole and C is called the center of curvature. On the surface, PC is the radius of curvature. You can see here this is the distance from center of curvature to the pole is known as radius of curvature of the surface. Let us suppose a point object O. Here you can see this is the point object O be placed on the principal axis of the surface. An incident ray of light which is OA, you can see here this is the incident light ray OA. After refraction at the point A on the surface bends towards the normal. clear, and goes in which direction? CAN. You can see here it goes in CAN. You can see here this is the refracted normal, and goes along AB into the denser medium. Another incident ray OP fall on the surface normally. You can see here another ray which is your OP. This is you also call it the principal axis, fall on the surface normally and hence goes undeviated into the denser medium. The two refracted rays, one is your AB and PQ, when produced backward direction, meet at which point? On the principal axis at point I. You can see here they all are meeting at the point I here, which is the virtual image of O. Clear? Fine. Now suppose the angle of incidence, that is your OAC, you can see here the angle of incidence OAC, this one, clear, is equals to how much? I, and the angle of refraction BAN is equals to R. You can see from the figure angle BAN is your angle of refraction, this one here. Let us suppose PO is equals to minus U and PI equals to minus V and PC is equals to minus R, clear. So all the distances are taken as negative as they are measured opposite to the incident line. As we discussed earlier, the distance which we are measuring in the negative x direction all are taken as negative, while the distances which we are considering in the positive x direction are taken as positive. Let us suppose alpha, beta and gamma be the angle made by OA, IA and CA respectively with the principal axis. Let a small h be the height of the normal and is dropped from A on the principal axis. Now in triangle COA, you can see in the triangle COA here, C to O to A, this is the triangle formation. We have gamma equals to alpha plus I, or you can also write angle of incidence is equals to gamma minus alpha. This is, again we are considering here triangle CIA. You can see in the above figure CIA, this is the triangle. What happened here? We have gamma is equals to beta plus R, clear, this. So we can find out the angle, refracted angle equals to how much? Gamma minus beta. Now we are again using here Snell's law, which is your sin I by sin R is equals to N2 upon N1, or you can also write it N1 is sin I is equals to N2 sin R, clear. For a spherical surface of small aperture, suppose if the aperture is very small, so the point A will be close to the pole P. You can see here this is the point A. If the aperture of the lens is very small, so this point come closer to A. What happen in that case? The angle is the angle I and the refracted will be very small. So the angle of incidence and the refracted angle are also very small. If if I and R are measured in radian, then sin I equals to how much? I, and sin R equals to R. We can take here. So in place of sin I and sin R, we can write like this: N1 I is equals to N2 R. Clear? Now substituting it in the value of I and R from equation 1 and equation 2, we have, you can see here, this is the equation number 1, this is I, and this is the equation number 2, which is your R. Clear? So from here we put the value of I and R in this equation. Where? In this one. So what we get? N1 gamma minus alpha and N2 gamma minus beta. So after arranging or solving, we get here N2 beta minus N1 alpha equals to N2 minus N1 of gamma. Or if point A is close to point P, fine, the point M will also be close to P and the angle alpha, beta and gamma will also be small. So what we can write then? You can see here in the figure, if the point A come closer to the point P, so that this point, this is M, is also comes very near to the point A. So the angle of alpha, beta and gamma will also be very small. So we can write here alpha is equals to tan alpha, and what is tan alpha is perpendicular upon base, that is your AM upon MO. Now since MO and PO is almost equal, because it is the distance, you can see here MO and PO. Clear? If the point M is very close to the point P, then the distance from M to O and P to O is almost equal. Fine. So we write here in place of MO, we can write here PO also, and AM is equals to how much? AM is your H and MO or PO is equals to minus U, because we are moving in the negative direction of x-axis. Similarly, if we are taking here beta, so 10 beta is equals to how much? 10 beta AM upon MI equals to AM upon, you can write in place of MI equals to PI, which is approximately equals to. So this is the distance we consider here minus V. Fine. Also you can write for the gamma, 10 gamma is equals to AM upon MC, where MC is equals approximately equals to PC, and this is the radius of curvature distance. So in place of AM we write H, and in place of PC we write here minus R. Clear? Now we put all the values in the above equation number 3 here. In this one, what we get here after putting the value N2 H upon minus V minus N1 H upon minus U is equals to N2 minus N1 H upon minus R. Fine. After arranging all these terms, N2 upon V minus N1 upon U is equals to N2 minus N1 by R. This is the relation. This equation relates U, V and R with the absolute refractive indices of the denser and the rarer media. If N is equals to N2 upon N1, you can see here, if N is equals to N2 upon N1 be the refractive index of the denser medium relative to the rarer medium, then the above equation you can write like this: N is upon V minus 1 upon U is equals to N minus 1 by R. Fine. So according to this formula, V does not depend upon alpha. Hence all the rays starting from O after refraction at the concave surface of a small aperture will appears to come from the same point I, that is I is called virtual image of O. Now as R is negative for concave surfaces, fine, so the value of V will also be negative for all negative value of R. This means that the image will always be formed in the first medium, and what type of image? It is virtual in nature. Clear? Now the same thing we will do here for the convex mirror. This is your convex mirror. If you can see, this is the for convex mirror, and the above relation we prove is for a convex mirror, sorry, concave mirror. Here refraction at convex spherical surfaces. So same thing we will do here. Let SP S dash be a convex spherical surface separating a rarer medium whose absolute refractive index is how much? N1, from a denser medium of refractive index N2. Clear? Let P be the pole and C be the center of curvature. This is the pole and this is the center of curvature of the surface. PC is the radius of curvature. Distance from P to C is the radius of curvature. Let us suppose a point O be placed. You can see here, this is the point O. We place at the principal axis. Now if we produce PC backward direction, an incident rays of light OA, you can see here, this is the incident ray OA, after refraction at point A on the surface bends towards the normal. Clear? CAN and goes along AI. Fine. In the denser medium, another incident ray OP, you can see here O to P, fall on the refracting surface normally and hence goes undeviated into the denser medium. So you know very well, when a light ray normally falls on a lens or a mirror, then it goes undeviated or parallel to the principal axis. The two refracted rays meet on the principal axis at point I, which is the real image of O. Where they are meeting? This, at this point I, this is the and there is the formation of real image. Suppose the angle of incidence, that is your OAN, fine, is equals to how much? I. the angle of refraction IAC is equals to R, and PO is your minus U, and PI is taken here positive because we are moving in the positive x direction. So distance from P to I is taken as positive, which is your V, and PC is also in the positive x direction, so we can taking here as plus R. According to the coordinate geometry sign convention, U is negative while V and R are positive. You can see here, let alpha, beta and gamma be the angle made by OA, IA and CA respectively, with which principal axis let H be the height of the normal AM drop from A on the principal axis. Now in triangle you can see in the figure COA here. This is the triangle we are talking about. In this triangle COA we have I equals to alpha plus gamma. Fine. Again we are taking here triangle CIA. You can see here and triangle CIA, this one CIA, this is the refracted angle. So we have gamma equals to R plus beta, or you also can write here R equals to gamma minus beta. These are the relations. So again same thing we did here, applying the Snell's law sin I by sin R equals to N2 upon N1, or you can write here N1 sin I equals to N2 sin R. Now for a spherical surface, if the aperture is very small, what happen in that case? The point A, this is the point A, come closer to the point P. Fine. The point A come closer to the point P, and the angles that is incident and the refracted angle will be also very small when the point A come close to the point B. Now if angle I and angle R are measured in radian, then we may put sin I equals to how much? I. Here you can see, and sin R equals to how much? R. So in place of sin I and sin R in this here, we write like N1I is equals to N2R. Clear? Substituting it in the value of IR from equation 1 and 2. This is the equation number 1 you can see here, and this is your equation number 2 refracted for refracted. So after putting the value, what we get here, N1 alpha plus gamma equals to N2 gamma minus beta. So after solving all the relations, you finally get here N2 beta equals to N1 alpha is equals to N2 minus N1 of gamma. So again for a small aperture surface, the point M will be quite close to P, and the angle alpha, beta and gamma will be so small that we may replace them by their tangents thus. So we here consider as a tangent there. After solving, alpha equals to 10 alpha AM upon MO, and MO approximately equals to PO. So here we get H upon minus U. Same thing we will did here. Beta is equals to 10 beta AM upon MI. So AM upon, we can write in place of MI equals to how much? PI. So we get here H upon V, and gamma equals to 10 gamma AM upon MC, or AM upon PC is equals to H by R. Clear? Now supposing we put all these trigonometric ratios value or alpha, beta, gamma value in equation number which one? Third. So after putting, what we get here relation, N2H upon V plus N1H upon minus U is equals to N2 minus N1 H by R here. Fine. So if you solve it, after you get the final relation N2 upon V minus N1 upon U is equals to N2 minus N1 by R. This is the required expression which is same for a concave spherical surface, as why we already proved for the concave. Now this is for the convex. Clear? I hope it is clear for you. If suppose that N be the refractive index of the denser medium related to the rarer medium, so we can write here like this, N is equals to N2 upon N1, and the above equation reduces to like this, N upon V minus 1 upon U equals to N minus 1 by R. So according to this formula, width does not depend upon alpha. Hence all rays starting from O after refraction from the convex surface of a small aperture will meet at the point I, that is I is the real image of O. So that's all today for this class today, students. We will cover our next topic, lenses, in the upcoming lectures. Till that, do study. Thank you class. Thank you very much.